Well, ladies and gentlemen, welcome to installment number, I don't know, 8, 9, I don't know, but it's chapter 7, Climate and Terrestrial Biodiversity. So we're going to begin today with a couple of fun facts. One of them I think you already know. If you're in my class, I think it was on a Jeopardy review game, but who was slated to originally play Terminator in the Terminator movies, but was eventually canned because they said no one could take him seriously as a ruthless, heartless killer. Do you know I can't speak. Do you know who that was? Not Arnold Schwarzenegger, who ended up playing it, but it was O.J. Simpson. Ironic, isn't it? Maybe they should have kept him. Okay, anyway, second fun fact. And hopefully, maybe you guys have heard it before. I don't know. I'm not sure. Did you know that you are 10 times more other things than you are you? What? What do I mean by that? This is what I mean. For every cell that makes up your body, there are 10 bacterial cells that either live on or in you. Whoa. Right? So you're 10 times more bacteria than you are you. What am I talking about? I don't know. Okay, so climate and terrestrial biodiversity today. What factors influence climate? Okay, so this is kind of a doozy. There's a lot going on, so I'll try and explain it to the best of my ability in a way that you guys will understand. Yeah, let's do that. So first, what is the difference between weather and climate? I'll give you a second. Very good. Weather is a short-term condition, right? What's the weather outside today? Is it rainy? Is it sunny? Is it cloudy? It changes within hours, within minutes, every day, right? Climate is an area's average weather over long periods of time. We're called the sunshine state because on average, we receive a lot of sunshine, right? Let's see, Seattle is known for rainy, wet, dreary days because on average they get a lot of rain, which we'll explain why later on in this PowerPoint. Right, so the climate is an area's long-term average weather pattern, okay? Weather local. Climate, see, over long periods of time, boom. If you need this one, pause it. I'm going to go skip through it. Okay, this slide has a lot on there. You're probably going, what is he doing to us? Okay, major factors determining air circulation. We are going to talk about all of these today, all right? So that's why I put summary slide, test yourself here. What I recommend is when we're done with today's lecture, right, pause it, come back to the slide, and see if you understand all of these things. So these are kind of like your objectives, and not only do you understand them, but can you elaborate on them in a meaningful manner and really explain the details of whatever is being shorthanded here, okay? So it's a good slide to test yourself. All right, so by the end of today's lecture, what we really want to be able to do is look at this map right here and explain why we see the biomes where they are, okay? So let's look at here, across the equator. We see a lot of green. Across this one, we see a lot of desert. Why do we have desert here in the middle of the United States? Why is there this highland mountain region here and the desert around here? All right, so why is it beautiful and green here, mountains and desert? All right, so we want to be able to explain the general patterns that we see and any anomalies. And this right here would be one of those anomalies, okay, in the United States. In the Midwest, why is it so dry there, okay? Okay, it went backwards, it seems like. Now, here we go. 3 factors that create wind. We're going to discuss each one of these independently. 1, uneven heating of the Earth's surface by the sun. 2, rotation of the Earth on its axis. And 3, air circulation is affected by the properties of air, wind, and land. Oh, sorry, air, water, and land. Sorry. Okay. Number 1, uneven heating of the Earth's surface by the sun. The sun, right, is not a flat wall. If it was a flat wall and the sun was shining at it, right, each square inch of that wall would get the same quantity of sunlight hitting it at one time. Because the Earth is a sphere, right, it curves towards the poles, and North and South Pole. That means that the area that is facing the sun most directly, like it's a flat wall, is the equator. And then as the Earth bends at the poles, the sunlight has to spread over those areas. Okay? So let me see if there is white location I can write on. Okay, let's do it here. So here is the Earth. Okay, here's the equator, and here is some of the sunlight. So imagine that the sun's rays come in these, I don't know, like tubes of sunshine, I'm not sure. It is going to strike the Earth, right, in that full quantity will be felt right in that location because it's direct sun rays hitting the Earth. Now, as we get, and I'm going to accentuate this curve a little bit just so it becomes clear. Right, now say this area right here. It's here, and it's here. Alright, that same width of sunshine, this is a terrible illustration, I'm sorry, is now hitting a larger surface area. Look how much more of the Earth it has to hit and be spread over when the Earth is curved as opposed to hitting a flat surface, right? So because that same quantity of sunshine is spread over a greater area because of the curvature of the Earth, the poles receive less solar energy, solar radiation, than the equator does. So the equator always has more energy than the poles because it's receiving more direct sunlight. Hopefully that was clear. Sorry for my terrible, terrible illustrations. And now let's move on. Number 2, rotation of the Earth on its axis, the Coriolis effect. Now we're going to come back to the Coriolis effect later on when we talk about, was it hurricanes? All right, and we're going to refer to it as the Coriolis force, okay? A pseudo-force, very weak. For here, at this point, I want you to know it as the Coriolis effect, on its effect on the bending of wind. All right, so it's called the Coriolis effect, and here's what happens. Wind moves on the surface of the Earth because of pressure differences. Okay, it moves from areas of high pressure to low pressure. And if you remember back to physics, that makes sense, right? Things tend to move in areas of high pressure to low pressure. And that's how our winds move. But our winds will move in straight lines because that's the pressure differences in the gradient that we see. So the air wants to move in a straight line. However, if you look in this map, it looks like the wind is actually bending. It's curving. But that is false to say that it is actually bending. It's all based on appearance. It's not reality. The Earth is not actually, the wind is not actually bending and curving. It just appears like it is to you when you're fixed on the surface of the Earth. And we'll explain that here in 1 second. Another thing I want you to notice while you're looking at these winds is that we name a wind based on where it originates. Not where it's blowing, but where it originates. So this westerly, it's called a westerly because it begins in the west, but it blows east. This is called a northeast trade wind. Even though it is blowing southwest, it originates in the northeast. So winds get their name based on their origin, not the direction that they're blowing. Okay, pressure differences tend to push winds in straight paths, yet winds follow curved paths across the Earth. So I left a blank slide here, so I had some place to write. This tends to be a sticking point for some people, and it becomes somewhat confusing for them. So, I'm going to say here is the Earth. I don't need the whole thing. Alright, and we're going to say that the equator is right here. Okay. If when I am done with this, you don't understand it, then you are forced to do one thing, and that is just to memorize that when you move, I'll say, I'll put it right here, away from equator, I'll put EQ, then you move away from the equator, the wind bends east. Okay? And you move away from the equator, the wind bends east. When you move toward equator, it bends west. Okay? So pause that here and write that down if you need to. Keeping that in mind, I'll try to explain to you why this phenomenon happens. And remember, this is not reality, this is just appearances, okay? The wind doesn't actually bend, the wind actually moves straight paths. But to you fixed on the planet, it looks like it's bending. So say, let me see, I'm standing right here. Okay? And this pigot is up here on the North Pole. And this pigot wants to shoot me with an arrow. Okay? If she, let's also draw this little line here, this arrow right here, meaning that the Earth spins, it rotates, right? And it spins, to you guys, orientation to the right. So it's always rotating this way, counterclockwise, okay? So if she were to shoot me, her arrow directly at me, by the time it got to where I was, it'd be behind me because I'm rotating underneath that arrow, right? Because I'm fixed to the Earth. As soon as that arrow becomes airborne, it's not fixed to the Earth. So it doesn't turn with the Earth, right? I still do because I'm still fixed to the planet. So if she really wants to hit me, she's got to lead me, right? So what happens is she starts aiming here. So she lets her arrow fly. And the arrow's coming, and to me fixed on the planet, since I'm moving into the arrow, it looks like it curves, boom, and hits me, right? It appears that way. It doesn't actually move, but it appears that way. Again, moving toward the equator, the wind bends left, or bends west. Now say I will exact my revenge on her, and she is somewhere over here. Okay? Now if I aim directly at her, same thing. She'll move, and I won't hit her. So I'm going to lead her. Now when I shoot this arrow, right, through this direction, as she is spinning towards that point, she sees that arrow coming, and as she's moving, it appears as if that arrow just bends directly towards her at that spot. By the time she makes it, bam, it hits her. So moving away from the equator, it appears as if it's bending east, okay? So hopefully that makes sense, and if not, just remember what I told you to memorize. Okay, number 3, global air circulation is affected by properties of air, water, and land. Okay, now we're going to come back to this later on. All right, and we're going to explain this movement that we see here. And we're also going to explain why biomes end up in certain locations based on this right here. So, wind. Prevailing winds blow over the ocean surface, resulting in currents. All right, we'll talk about currents later on. Wind is the result of horizontal pressure differences in air. We discussed that. And air flows from areas of high pressure to areas of low pressure. Correct, we covered that as well. This information about convection cells, I'm going to explain to you the next few slides. So again, come back to this and read it when we're done, and make sure that you got all of this from the lecture. And if not, then read through it until this becomes clear and self-evident. Now let's go back to here. Nope. Okay. Movements of air along the surface of the Earth are due to pressure differences. It wants to move from high to low. Vertical movement of air is caused by temperature differences. Horizontal air movement is pressure. Vertical is temperature. Okay? So this air, imagine this is the equator right here. It's very hot. So the air gets super hot and it wants to move vertical, right? Go skyward. Because all that air wants to move away from this corner, there's no air there, right? Because it's always trying to move away from it, so that's why this is a low pressure corner. As this air moves vertical, it's hot and it's wet, right? It's blown, it's moved across the surface of the Earth and the oceans, has picked up moisture in its travels, is now super hot and wet, and it goes skyward. Now, as it finally makes it into the upper troposphere, right? Because before it gets to the troposphere, but it hits the stratosphere and it bends, it moves. It can't really make it into that stratosphere. So it reaches the top of the troposphere. It's cooler up there at the top of the troposphere. So now this air is no longer hot, right? It's become colder. And things that are cold, air that is cold, has a harder time holding on to moisture than the warm air does, right? Because the air molecules move closer together, there's less space to hold that water. So when it gets here to the troposphere, the top of the troposphere, all that water condenses out and it falls. And it falls back to the surface of the Earth right here. So at this location, what type of biome would you expect to find? I'll give you a second to think about it. Good. If you said forest, specifically tropical rainforest, if this was the equator, like we said, then you're correct. So this area on the ground is already hot and warm, and then all this rain falls here because it condenses out here at the top. So that means it's hot and it's wet rainforest. Now, it starts to bend, and it rotates here until it becomes cold enough now where it wants to drop. Now all right, so obviously, all the air is going here. It's moving here, that's why this is an area of high pressure. So then it wants to spread out, so it wants to go from high to low. So it moves towards the areas of low pressure. And when it gets here, it's so cold that it wants to drop again. So because it's dropping, it all wants to drop here because it's so cold, this area is a low pressure area. And since it all moves to this corner here, this area is high pressure. Now here's what happens as the air drops. As it starts to descend and get closer to the Earth's surface, the surface of the Earth is much warmer than the upper troposphere. So now this air gets warmed. So warm. And it's dry, right? Because it dropped all of its moisture over here. So by the time it makes it to this corner, it's warm and it's dry. So what type of biome do you think exists in this corner? Think about it. If you said desert, then you're correct, right? So we've got a desert in this high pressure area, and we have a tropical rainforest in this low pressure area. Now, there's a pressure difference, so the air wants to move across here. As this air moves from this high corner to this low corner, it picks up some moisture along the way, right? Because it's got to have a lot of moisture here when it gets to this corner. So as it moves across this area, it picks up moisture and it drops some along the way as well. So as you move from this desert to this forest, in the middle of it, you end up having grasslands, areas that receive some moisture, but not a lot like this corner does. So desert, forest, grasslands, okay? And that brings us to these things called convection cells. So heat and moisture are distributed over the Earth's surface by vertical currents, right? Because of temperature differences, they make the vertical. And they form 6 giant convection cells at different latitudes. Right, so there are the Hadley cells, Ferrel cells, and polar cells. So these cells that we're discussing right here, right? Imagine this thing coming up and around and moving all the way across the surface of the Earth. And they happen every 30 degrees north and south latitude. Right? And we have 6 of them. 1, 2, 3, 4, 5, 6. So this one basically starts here at 0 degrees latitude and goes to 30. One of the Ferrel cells starts here at about 30 and goes to 60. So they go every 30 degrees north and south latitude. The two located towards the equator are our Hadley cells. This one right here and this one right here at the mid-latitudes, 30 north and 30 south, are the Ferrel cells. And then the two at the top, polar and polar. Okay? So you can see right here, see this air is moving this way and then rises up. Based on these arrows, we can tell that this air is going to rise up here at the equator. So it drops all of its rain, if you remember that the cell we just looked at. So right here, look at that. Forest. Where it descends, desert. Now this cell moves in the opposite direction of this one. So this air actually comes here, and so they bend the same way. If you look at my twirling fingers, right? So where this air is coming down as well, it's also falling over that desert line. And then where it comes up over here, these are our forests up north. Instead of having tropical, subtropical forests like we do here in Florida and in, say, South America, up north they've got temperate deciduous forests. And that's where we find these, all right, based on these cells. Another little fun fact for you guys is the, what is it here? The feral cells, I believe, are an area in the ocean where there's not a lot of current and wind that is experienced. Sometimes there's great current, and other times it's just like dead right here where this air is coming down, and there's not a lot of wind for the sailors back in the day to use to sail their ships. Right, so they often called those the horse latitudes, because if you were at a time of year where those convection currents were very weak, right, and therefore there was not a lot of downward moving wind, then you were stuck out there in this location, 30 degrees south latitude, until those convection cells got stronger and you could catch that wind. All right, maybe it was a couple days, maybe it was up to a couple months. So what would happen is those people on the ships, to lighten the loads, they would throw over cargo that they did not need at that moment. Horses in the middle of the ocean are not needed, required, so they would often dump them, throw them into the ocean when there was very little air movement. It lightened the load of the ship, and they could move faster on less air current. So those are often referred to as the horse latitudes. That little fun fact comes compliments of Miss Piggott. If you don't know why she knows so much about the ocean, ask her about her history. Okay, so oceans and currents. Oceans absorb heat from Earth's air circulation patterns. Most heat is in tropical areas because it's near the equator. That makes sense. Heat and differences in water density create ocean currents. Okay, cold, dense, salty water sinks. Warm, less dense, less salty water rises. Okay, so just like those air currents are moving over the surface of the ocean and over the earth, what happens is they actually literally are blowing over the water, and they are moving and creating these currents in the ocean, right? And the equator is the water is very warm, so it's less dense and it's on the surface. And as it's moving, and it would move in these same straight lines as well, but there's continents in the way. So these currents are forced to move and turn and move around the continents, and that's what creates these crazy ocean currents that you see if you were to go to Google and do a Google image. Do it. What happens is, as the water from the equator moves towards, it hits, like say, North America, and is shunted or moved into the polar areas near Canada and Greenland, right? It becomes very cold, and then it becomes more dense, and it actually sinks to the bottom of the ocean and then comes back towards the equator, continuing that conveyor belt system of ocean currents. So all of this is based off of the greenhouse effect. Without the greenhouse gases, here's some of them over here: water, carbon dioxide, methane, NOx, just know that as NOx. They all hold on to some of the Earth's heat, and that is what creates these temperature differences in the air, temperature differences in the ocean, which helps everything cycle and spread the warmth and the cold of the Earth. So we need the greenhouse effect for life. Without the greenhouse effect, there would be no life on the planet, right? Some areas would be way too hot and areas would be way too cold. So what you need to know about the greenhouse effect that is most important is it occurs because the light, solar energy from the sun hits the planet. The Earth itself absorbs that short wavelength, high energy solar energy, and then what it does is it re-emits it as longer wavelength, lower intensity, radiant energy. Radiant is another way of saying heat. So it is the Earth that re-emits that solar energy as heat energy that then gets trapped by those gases that surround the planet. Just a few more things. Earth's surface is affected by local climates, breezes, coastal breezes. Like my parents live right near the ocean, so it is always a little bit cooler for them in the summertime because they're getting the breezes created by temperature differences on the coastline and the wind moving in to land and off the land. So uneven heating creates land and sea breezes. It's lovely there. Rain shadow effect. This helps explain the desert that we see in the Midwest U.S. and the fact that that's a grassland and very dry. And I'll explain to you in another slide as well. But here's what happens. You have these air currents coming off of the ocean, which means if they're coming off the ocean, they probably have absorbed a lot of moisture, and they have. They hit the land, and then they are forced over this mountain. Well, as this air is rising over this mountain, it's forced skyward, right? And as we said before, as things get higher in the troposphere, it gets colder. Cold air can't hold on to the moisture, so the rainwater actually drops out of the air on this part of the mountain, right? By the time it gets up to the top, it's dropped all of that moisture. So the windward side of the mountain is green, lush, beautiful. The leeward, L-E-E-W-A-R-D, the leeward side of the mountain now gets air that is dry. So when it comes over this other side, there's no more moisture to drop because it already did on this side, right? So because it's dry, you get these arid conditions on the opposite or leeward side of the mountain. And that's what this basically is saying. So you can pause it here if you want to read it. So now let's look back at this. Okay, this is the equator. We would expect, because of that, the Hadley cells, that the air is rising here, so we should see green, lush environment along this area. We do. That makes sense. Here at 30 north and 30 south, we should find some deserts along the way, because that's where that air is descending and now it's dry. And we do. Look at that. Beautiful. So that is great. So that kind of explains why we find those biomes in those locations. Now, however, why do we have this desert region here? Well, here is these currents that flow this way towards the west United States. They're hitting California, dropping their rain, usually, even though they're having a terrible drought right now. And that's why the coast of California has been a great place to grow crops for a long period of time. Perfect conditions. And that's also why Seattle is always rainy and dreary, right? Because they really get hit by these currents. And as they flow over the Sierra Nevada mountains, it drops their rain, it flows back down, and you end up with these grasslands and some desert conditions in the Midwest United States. There's no more moisture in that wind. And then same thing over here. Here's the Himalayan mountains. And as the current, as you see it's coming here, hits here, it drops all of its rain, rises over the Himalayas, comes back the other side. There's no more moisture, so there's a giant desert that is in a huge part of China. I believe that is it. It's probably a long, extensive one, and I apologize. Hopefully you understood everything.